In every generation, there comes a technology that changes how we see the world and ourselves in it. It changes our values, how we live our lives, and how we learn. It changes how we interact with each other and how we interact with it. Welcome to the radically connected, data-driven digital world, where everything is always on and moves at the speed of now, where it's not about just keeping pace, but leaping ahead. The new wave of dominant enterprises are powered by data-driven DNA that lets them engage their customers like never before, at any time, on any device. As the leading distributed database technology, DataStax can infuse the same data-driven DNA from internet giants like Google and Amazon into your online applications, giving you the technical capabilities to leave your competition behind. When millions of viewers access the future of television, DataStax is there. When home appliances become lifestyle changers, DataStax is there. And when online entertainment consumes more than 2/3 of internet traffic, the DNA of internet leaders is making sure that everything is always on, no matter what. It's all made possible with DataStax Enterprise, powered by Apache Cassandra, delivering the confidence that your business can scale to any size on systems that will never go down. With DataStax, online shopping becomes more personalized. Electronic banking is safer. Entertainment is streamed in the blink of an eye, and social media feels a lot less crowded. It's a new world where online applications are deployed with maximum velocity and cost efficiency, transforming data into real-time insights that fuel innovation. Becoming an internet enterprise is a modern-day imperative that creates dynamic interaction and makes every customer feel like they're your only customer. Join the world's most innovative companies. Become an internet enterprise with DataStax.
Good morning, everybody, and welcome to our European Cassandra Summit of 2014. It is really, really great to have everybody here today, and it's a pleasure to be here. We come from the Bay Area in California, not just for the warmth and the sunshine of London, but also because there is really something special that's starting to happen here in terms of the Cassandra community and the momentum that's being created by everything that you all are doing, with the fascinating things that we see from the use cases from customers of all shapes and sizes. And if you think about just where we are today from just a few years ago, it's pretty amazing. We know of over 6,000, well over 6,000 active community members that are happening right now here in this area. And we estimate there's probably 4 to 5 times that who are not yet part of our lists and our meetup RSVPs, but this represents an explosion from where we were just a few years ago. We also see today, with over 1,000 people registered for our summit, that we have an intense interest for people to get together and to share and to learn and to see what's really happening and how they can accelerate their learning. And in that, we will have over 30 sessions today that are jam-packed full of information that we want to be relevant. And we want it to be something that everybody can see the progress and learn, because one of our biggest challenges today actually is not the technology, it's the ecosystem. It's getting things to grow and expand quickly takes talent. And the talent that we have here in the room today represents that catalyst that can help grow this industry. The talent getting together right now represents really the power of creation, if you think about it. Because you have the talent and the stuff to come together and then explode out there into an amazing new world of technology and an amazing new world of applications. This is real. This isn't theoretical. When I get to hear so many things that are happening and how industries are changing, and you're going to hear a little bit later about how actual lives are being changed by what you are doing. You're creating this new world, and it's fantastic and it's exciting. It's probably the most exciting time that I can remember, but we owe this moment to a lot of different people like yourselves who have been here through varying stages of our growth. So it would be a little American of me to not take a moment and thank some people who actually got us here. And I'd like to do that on a timeline and look at it in terms of groups of people who've been working with Cassandra for years. And if we think about our first group of people, these are our old timers. This is represented by the lovely and talented Mr. Jonathan Ellis here on the screen, who's the Apache Cassandra chairman. But this group represents pioneers. And in this group, if you're in this group, we owe you a tremendous amount of debt. Because you had the foresight and the fortitude at a time when anything was up for grabs, technologies were springing up all over the place, but you dedicated yourselves to making Cassandra something really special. And that brings us to a second group of people, represented by folks like Emily, who joined us a couple of years ago. And if you have more than a couple years of experience with Cassandra, you're a card-carrying veteran, because this industry moves so quickly. And what's great about you in this group is that you took the technology from the shadows and you brought it into the light. And now it could be seen and start to be propagated and used for all sorts of new things. And then finally, we have new people who are joining us right now, represented by folks like Gary. And maybe you're just here for the first time learning about what does Cassandra mean to me? How can it help me in my career? But what's great about this group is this group takes it not from the shadows into the light, but from the light into the mainstream. And that's what we're seeing with these applications, moving into everyday usage in traditional companies and startups alike. You're here because you're making a choice. You're making a choice with your time, you're making a choice with your talent, you're making a choice to invest in something that we believe is going to be industry changing. And as the old saying goes, life is about choice. And if we think about the context of what's happening today, I want to take us back in time and view a little bit of past as prologue. And I want to take you back some 20 years. Now, I'm very aware I am in Europe and we have a European audience, and as such, when I say football, that probably means something very different to you than it means to me. But I was a college football player, you would say university here, and in the United States, college athletics are a very big deal. I was fortunate enough to have a scholarship, and I played American football. And my friend group looks something like this. These are the types of folks I hang out with during the day when I played on my team. Some 6'4" or 5", 300-pound fellows that probably would not attend a conference like this. But I was also a computer science major. And as a computer science major, I had a very different set of friends by night. And the friends group really did not mesh well. And so I kept them distinct. And when times would come when we were going to go out and do something at night, I made a choice. Which group did I want to be with? But in 1992, when I graduated, there was a different set of choices ahead of me that would actually shape the whole destiny of my career for the next 20 years. And that was this. On the one hand, if you're old enough to remember this piece of hotness, this is an IBM ES9000. And it was all the rage back in 1992. It was an innovative and powerful piece of hardware that ran a database called IMS. And an IMS had been around for over 20 years, and it was the established standard. This is where I was told my future was as a computer science major. Put my time, talent, and energy into this world because this is where all the mission-critical stuff happened, and that was not going to change. But there was a problem. There was a new technology that was emerging, and this is something called a Spark Station. We used to call them pizza boxes. And this ran something that represented a change, a shift from the way we thought about working with our data. And it wasn't so much the Spark Station or Unix that infatuated me, it was this technology called Oracle. Because in 1992, Oracle released version 6. And in version 6, some really groundbreaking things started to emerge called referential integrity and functions and procedures and triggers. Suddenly, we started seeing the world a little bit differently in how we related to our data. But make no mistake about it, I lived at that time in what's called the Midwest of the United States. And the way the technology waves occur in the United States is it's very coastal. So the West Coast is often the birthplace of much of the technology. East Coast adopts it very quickly. And then we have this area in the middle that moves a little slower and takes more years to adapt. And so in 1992, this was a very real choice. And we ran into very real problems inside of organizations around battles that would take place over using the new technology versus the established technology. And I think that that is a very similar place to where we are today. And I chose the route of the Oracle world, and it was fantastic. because that led us into this era of the relational databases and eventually into client server. And relational databases were fantastic. They gave us a new way to look at how our data related. So I, as a person, would be in a database, and I would be a part of an ER diagram. I would have attributes about myself, date of birth and address, and I might shop at a store, and that store would have attributes, and there would be products in a store, and we all related together. This is old news to most of you in the room, but some of you in the room are probably so young, you're not even sure what an ER diagram is. Go look it up on Wikipedia afterwards. Pretty interesting stuff. But something is changing. There's a fundamental change that's occurring right now. And there's a lot of reasons for it, but I think at the core, there's one element that if we really drill down into it, it's this notion of no longer looking at our data in static points of disconnected time, but instead moving through life, moving through time with our data as an integral part of every decision and every action we take. And this is simply a world that was foreign to the creators of relational databases. I often say, because sometimes people think I have it out for relational database, and I say, no, they're not that they're bad, they're just antiquated. They're from a different era. And as you shift the way you work with data, you must shift the way that you think about managing that data. Moving through time means things change, requirements change. And suddenly you go from this world of somewhat connected to being radically connected. But in a paradoxical way, it's not just being radically connected, it's also being fully distributed, because you cannot handle the scale and the performance of this new demand on your data if you think about it the old way of scaling things up. And trying to fully distribute something while at the same time making sure that it stays radically connected is challenging. But this is the essence of what Cassandra is. And if you start to peel away the layers and get behind all the smoke and mirrors of NoSQL and what is it all about, the deeper you probe into a technology like Cassandra, you find at the core, it's that beautiful architecture that makes it so special and makes it so different and makes it so appropriate for this new world in which we live. And what this means is something pretty radical to you from a career standpoint, to your businesses from a business standpoint, and to the industry at large. And so I'm going to give you 3 numbers to help you try and categorize and think about what this means. Because even if you are some of the most technical people here, if you work for a larger company, odds are at some point you're going to get called in the conversation where somebody in that organization is not happy about all these changes. And having a good framework and a good dialogue is sometimes very, very helpful. So when I think about 20-60-20, I think about it in terms of a bell curve. And you could take about 20% of your workloads that I think are going to be statically very well equipped for relational workloads for the next 15, 20 years. We probably won't touch them. There are systems that I wrote in 1993 and 94 that are still in place today, and they probably won't change for another 5 years. That's fine. There's a very long tail in those kind of markets. But that's not why you're here. You're here for the new 20. And there's a new 20% or so of workloads that are emerging that simply disqualify relational databases from use. And I want to talk about one of those today. Really interesting company that we work with called Amara Health. And Amara Health Analytics does something special around a condition called sepsis. And sepsis is a blood disorder that occurs when an infection in your body gets so severe that your body starts just shutting down its organs to the point where you will eventually just die from it. Unfortunately, I have some firsthand experience with this with a family member. He's okay, he made it through, but it was a horrible experience for us. Because I still remember the doctor walking in and saying, we've induced a coma, we're going to leave him in the coma for 3 or 4 days, we're going to pump him full of antibiotics, and we're going to hope that we can relieve the symptoms of the sepsis, but his body has to do the work. And I remember at the time, this was about 6, 7 years ago, I remember at the time asking, is there really nothing more we can do? And the doctor looked at me and said, the problem with sepsis is you can't treat it until you know you have it, and you don't know you have it until you have it. And so once you reach that point, it gets too difficult to treat in any effective way. But Amara Health started with this problem and said, we have a better way of doing this. And they began with this notion of, obviously, a patient. A patient walks into a hospital. They have all the normal information that goes nicely into a relational database, but immediately they said, we need different types of data. We need that data from the healthcare providers. We need those nurses' notes, those doctors' notes, those things that create this semi-structured data or unstructured data. That was the first disqualifier from the old world because it didn't fit very well in that type of model. But then the next thing they do when you start to get sick is they start plugging on sensors all over your body, and those start feeding information. And what Amara Health said is, if we cannot look at a patient in discrete points of time, but instead actually walk through that entire stay of that patient through time and analyze that through time, what we can do is get to a correlation point that a human could not do. They can't compute it fast enough. There's too many variables. And we can alert the caregiver that a sepsis condition is likely to occur in the next X hours or days. And now they can intervene early. But this notion of being able to handle that kind of data flow and dealing with data through time instead of in points that are static and discrete changed the requirements for their system. And that's why I said at the beginning, this isn't just industry changing or career changing. This is going to alter the very nature of our life in terms of how we do things with our data. So that brings us to this middle 60. And the middle 60 is what I call the jump ball. And that means that there are systems out there today that are traditional systems that have run on traditional applications for a long time. But the challenge for many of your companies here today is, how do I compete in an era where everything is changing so quickly around me and the disruption is occurring largely from the internet companies? They were the ones who were the progenitors of most of this technology. They got to start from scratch. They didn't have the legacy applications to deal with behind the scenes, and so they are disrupting nearly every industry. You're going to hear about two in just a few minutes, very traditional industries being radically disrupted by this approach. And so the real challenge is, how do you take a traditional company and find a way to deliver the potency and the power and the data nimbleness of an internet company? That is a non-trivial problem. It requires new and different ways of thinking. It requires new and different technologies to make this happen. But it is absolutely possible, and it's happening around us now at an accelerated pace. And this is where you're going to hear a lot of over the next few days. One example is a grocery store that we work with. They do a little tour with us where we go out and talk to different companies and people trying to learn, and they take out their old loyalty card, which was the little barcode scanner at the time of checkout. They would scan it. Again, that's that whole thing about point in time and discrete. And then he tosses it aside, and he says, that's not how we do it anymore. Pulls out his phone and says, this is your new concierge as you're doing your shopping. Now you keep your lists, you keep your offers, you keep all of the things you want in your hand, and when you walk into the store, it even goes one step further, and thank goodness for people like me, it actually navigates you through the store to the shelf to pick up your things in an optimal path so that you don't waste any time at the shopping location. That's fantastic. That's a really old industry, grocery shopping, that's being upset by this technology and being radically changed at the same time. And so this is really the challenge for you. And you have this power, as I said, to create this new world. You are going to write our future. I don't know what the future is going to look like exactly. I can't tell you exactly when and how all of this is going to manifest. But what's great is I know the authors. I get to see and talk to people like you all the time. And you hold today in your hands the power to create a world that my future and my kids' future, they're going to live in for the next several decades. And so it's exciting and it's a privilege to stand here and to be able to talk with you and share with you and help with a conference like this to accelerate your ability to go change the world and to go make this happen. And with that, I'd actually like to move to hearing from a couple of your authors who are in this with you and who are doing some really cool things in some new ways. And we're going to start with, as I said, a very old industry, the financial industry. And would you please join me in welcoming to the stage Mr. Zohar Melamed If you want to come up and talk to us, Melamed. Hi, Zohar. How are you? So, Zohar, thank you so much for joining us here today. And why don't we start by just giving a quick background on who you are and what you do at the bank?
As it says, my name is Zohar. I work for Credit Suisse, a big financial global institution. I work in the investment banking division, and I'm the CTO for the equity derivative business globally. And my speciality within the organization is around risk management technology for the equity business globally. I think, interestingly, what you just said a couple of minutes ago really chimed with me in that this is my official job description. You know, this is what's on the blurb, on the bio. But if you really ask what I do, you know, what I actually do is, you know, over the last 6 or 7 years, I think I'm a bridge between the internet, the scale, the dynamism, you know, the economics, and the internal reality of, you know, a large multinational IT shop, and bringing that kind of technology to bear on the problems that we solve through the difficulties of doing it in a large organization. You know, that's the reality of what I do.
So being in a bank is fascinating to me because it's a complex institution with a lot of different complex offerings and services. But yet at the same time, we see often the financial industry is leading the way with some new technologies, but you also have to manage an incredible amount of risk because you can't afford to make the same mistakes that, say, a grocery store could make. Yours are going to be a lot more visible and a lot more painful. So could you tell us a little bit about when you make a step this big to move into a new technology, what drove you there? What were some of the things you assessed? How did you learn? And ultimately, how did you decide on which technologies to use?
I think that's an excellent question. And we've been using this technology in one of our major platforms, something that we've put together over the last 5 years or so. And if you'd asked me 6 years ago whether we could have built or we would approach building a platform of this magnitude of significance without any relational technology, you know, I would have laughed out loud. I think it was probably inconceivable that we would even consider that. Not just technically in terms of, you know, where the comfort zone was for the engineers, but certainly organizationally, you know, it was a very big ask. But I think there are two factors there. One is when you look at the technology that is there are some problems that we've historically encountered for years, you know, building these complex systems, which this technology really puts to bed for us and really gives us a leg up. And I think the other thing, when we sat down and looked at it, we said, well, you know, we want to build a system for the next 20 years, not for the previous 20 years.
Yeah.
And when you look at that and when you think about it that way, whatever organizational standards you happen to have in place at that point in time are really just a reference point, and you have to look at them and say, is that really the way to go? Where will I be in 5 years' time? Is that really where I want to be? You know, did the thing that we do last time round, you know, 10 years ago or so on, is that really the place to go? And we made the decision not to do that. And that was a decision that was made, as I said, you know, 4 or 5 years ago.
Yeah, which really isn't that long when you think about the time it takes to get the resources trained and the right talent in place and learn as you go. What were some of the challenges or obstacles that you had to overcome in those early days?
Yeah, I think it's not called disruption for no reason. You know, disruption is disruptive, I guess.
I think you told me earlier it wasn't polite.
There is no polite disruption. You know, I think it always represents a challenge. I think for the organization as much as for the engineering team. And I think inevitably in large organizations, innovation and disruption of this kind of nature happens bottom up. So it's very rare for traditional organizations, large corporations, to have this gentle disruption coming down from the top where someone makes that decision and it's communicated to the troops and people go and follow that. And the challenge for a large organization is, how do you integrate that? How do you make that happen within a very tight, within a very highly regulated and audited and controlled environment? You can't take any risks, as you quite rightly said. It's not a grocery shop, and we have to work within a very tight framework of controls. And at the same time, you don't want to stop innovation. You know, things. You know, if there's one thing that's guaranteed, is change. You know, nothing else is guaranteed. And so, I think as an organization, from a technology perspective, over these 5 years, we've been in this transition to a grassroots innovation model where the innovation model is much more federated. And we look at people experimenting and innovating, and we'd like to give people more space to do that, and at the same time move away from an illusion of control that you have in a large organization to a reality of visibility, and really seeing what people are doing, is it working, and very, very quickly be able to triage that and say, okay, this is good for us, this thing is not good for us, and we really want to stick to these few technologies and move ahead with them.
So that, you hit on something there that is, I can tell you is so incredibly common that we're finding in more and more organizations, that illusion of control versus the reality of the visibility. If you were to pass on some of your wisdom that you've learned in going through this now for the last 3 to 5 years, give it to us on 2 levels. First, maybe from the business perspective, because what we're seeing is now this is as much about business problems as it is technology problems. And then maybe from the technology side, final thoughts of wisdom that you'd like to pass along.
I think as I said, from the organizational perspective, there's been such a great shift. I think this is one of the last certainties. As you said, when you came out of university, there was a big box, and that box was going to stay there forever, and this is your future. And I think that is an area that is now at such a level of disruption and changing so rapidly that from a business perspective, I think being open to doing that and understanding that and going along with that and letting people experiment at the grassroots and having this federated model of innovation is essential for the business. And I think ultimately the economics, the dynamism that come along with that are imperative ultimately to be competitive. Being able to deliver solutions rapidly and at the scale and the cost that we need to. I think at the technical level, it's really just about understanding that when you take the risk, what kind of risk you're about to take, that there is a community that you work within. I think historically people felt much more comfortable going with a product that has a vendor behind it. It's the same today, but I think we like to see that together with a large community, a large open source community. And I think that's played extremely well for us on the technical side.
That's great. I think there's an obligation, maybe one final thought from you on as you federate and as you allow the teams to explore, what's the obligation of that team to interface back with the proper business to ensure that communication stays strong?
Yeah, so I think that's really where we were talking about the visibility, the really thing that's critical, and I'm sure you've seen that in many organizations. Typically, that visibility is done secret. That innovation is done secretly, or it's done in a kind of in the corner where no one sees it. And the real challenge organizationally is to open up that communication link to make sure that people are not scared, that people are happy to come out and be visible about what they do, and I think about the success of what they've attempted or the failure, so you can really, really learn from that.
Fantastic. Zohar, Melamed, thank you so much. Really appreciate you joining us. We've had the privilege of working with Zohar and his team for a while now, and those nuggets that we get from people who have lived through this are becoming more and more common. And this next individual is somebody who confronted that same problem at British Gas, and they took a federated approach, but boy, they really took a federated approach. So please join me in welcoming to the stage Mr. Jim Manning. So Jim, had a great opportunity last night with Jim at our executive track to go through a full presentation. I will tell you guys in advance, I told him I was going to throw him under the bus. If you can track him down later in the day too, he's got some amazing slides of some stuff that they do as data scientists in their world. But before I get there and get you harassed all day, give us a little bit of background on who you are and what you do.
Yeah, so I'm Jim Manning. I head up data and analytics at this amazing organization called Connected Homes, which was set up by British Gas 2 years ago. Career-wise, it's been pretty eclectic. I spent the first half of my career doing some very traditional corporate stuff around technology change. Then a mid-career crisis, went off, rented a house in Spain, taught myself to code, came back to the UK, founded a startup, 3.5 years, bombed out, kind of look back on it as the longest and most expensive training course of my life.
Education.
But during that time, I got really sort of interested in data and data visualization and what we could do with that. Then met the guys who were setting up connected homes, and boy, have they got some interesting data. So I've been doing that for the last 18 months, and it's been a blast.
Great. So we heard Zohar talk about how his team moved to this federated approach. British Gas, I think when we hear that name, or certainly when Europeans hear that name, it connotes a lot of information about a big, old company, been around a long time. How did we get to connected homes out of British Gas? And tell us a little bit about that journey and why that decision was made.
Yeah, so I mean, British Gas is I think about 185 years old. So in terms of an established company, it looks like what you think of it. But I think when maybe 3 years ago they were starting to see this kind of new category appearing of the connected home. And clearly, there are correlations between being an energy company and being in people's homes and being a company that people trust to go into their homes. There are 10,000 kind of expert engineers in British Gas. They visit 50,000 homes a day. So already had that presence in the home. So a connected homes proposition kind of made sense. But what they did was amazing, really. They set up this organization called Connected Homes. They made it a very, very separate thing. Separate offices, attracting different talent. It's about a 30-70 split between people who came from British Gas and people who came from outside. And they've just created this amazing environment where we have the freedom to innovate. So we've focused on 3 things. We've built a product called Hive Active Heating. So Hive lets you control your central heating from your phone. And it kind of sounds an obvious thing to do. And
it's a technical audience, so when we say Hive,
we don't mean that Hive.
Okay, no, exactly.
Hive Active Heating. So tonight I've got no idea what time I'll get home, but I know that about 15-20 minutes before I get home on the train, I can switch my heating on. My house will be warm. I'll have hot water, and I won't have spent a load of money heating an empty home. And I think what we're finding is as people get this technology, they can't just expect it. Why wouldn't you want to be able to control things in your home from your phone? And I think that experience has now kind of led us to think about, what are all of the other things? And I think there's a really exciting future with that product. One of the other things we do, smart energy report. So we take data from smart meters, and then we use that data to try and help people get a kind of real in-depth understanding of how they use their energy. There's a stat, I think, most people kind of interact with their energy company for less than 10 minutes a year, and that's normally when a bill lands on their doorstep.
So 8 of those 10 are being frustrated at your bill, right?
Absolutely. So creating a kind of better dialogue with your customers and helping them genuinely understand where their pounds and pennies go kind of puts them in control and lets them make the choices that they need to make. Then the other thing we're focusing on is something called connected boilers. So central heating boilers have maybe 30 or 40 different sensors inside them. And so we're connecting those sensors back to our data centers and then being able to use that data to really help with customer experience. When you've got 50,000 home visits a day, being able to make that a better experience for a customer who's got a broken down boiler is a fantastic thing to do. And our plans in the future are to develop the data science to predict that failure in advance, which is going to be awesome.
I think what you're doing and what Zohar are doing are so representative of this internet enterprise concept. He talked about being the conduit of making that happen. You took it to an extreme, started a whole new sub-company around it. What challenges did you face along the way in the very brief journey thus far with Connected Homes?
So, I mean, I think, I think because of what they did in setting up a separate thing, we haven't had to face some of the challenges that I guess other people in the room have. So, we have product guys set next to technology guys. We don't have this. We don't refer to the business as a separate thing. So I think that's really, really helped. Clearly, we're doing something new. Clearly, there aren't like hundreds and hundreds or thousands of people out there that have done this. So we have had a bit of a roller coaster in terms of the technology. But we're getting there. We're resolving it. I'm really lucky to have a really smart team of people working on those things. So yeah, I think we've kind of worked through the challenges. We're iterating fast. It's okay to fail, and we learn fast.
That's great. So what's next? I think that you guys have done an amazing job already, but you have pretty big visions on what's coming in the future. And how does that relate to the technology?
Well, I think, I mean, in terms of the technology, if you take this Internet of Things thing, and depending on who you talk to, people are saying by 2020 there might be 50 billion connected devices, or there might be 200 billion connected devices. So taking that and then adding that to the volume of data, adding that to the kind of data science that you want to do, we kind of get this sweet spot in the middle of those, which for us is Cassandra and Spark. So we're kind of really excited to be using that technology. In terms of the what's next, if you think about it from a customer's point of view, it's kind of two things. It's what's happening in my home, and put me in control. So building a product that says hey Billy, your central heating broke down yesterday, is futile, because you're going to be, yeah, I know, I'm cold, I haven't had a shower. But building a product where we can say, hey Billy, it looks like your central heating boiler is going to break down next week. We've got an engineer in your area next Thursday. Are you around? Can he come around and fix it? That's a really great customer experience. And then from the energy perspective, right now we're in the game of last month. This is how you spent. You spent 20% of the money you spend on your bill on cooking. But how much more useful to say to someone, hey, you've just left home, and the energy you're using right now is abnormally high for when you normally use home. You might want to go back and check whether you've left the oven off. So it's building that kind of real-time.
And then eventually just turn the oven off, right?
Yeah,
instead of going back and checking.
Absolutely.
Yeah, it's fantastic. What about final parting thoughts of wisdom? You've been on that roller coaster for a while. If you were going to leave us with one final thought, what would that be?
I think for me, it's working with the right people. When you're innovating and when you're trying to do things fast, you need to have a team around you who are smart, got smart technical chops, but people that aren't afraid to experiment, people that learn fast, and people who are okay working in that environment where sometimes you're going to fail. And I've just been so lucky to be able to get that team around me, and lots of them I think in the audience today. So if you guys get a chance to talk to those guys, do, because they're all really interesting people. Don't poach them, you're not allowed to do that, they're mine. But yeah, definitely, it's the people, the technology, I think, is the foundation. And we can always, the technology will always evolve and will solve the problems, but in order to move fast, it's, get the right people around you. Absolutely.
Great. Jim, thank you so much.
Thank you.
It's been a real pleasure. As I said, we're getting to watch this innovation happen in industry after industry after industry, and this concept of taking those traditional enterprises and allowing them to move and act with the speed and the power of the internet companies is what is really shaking up everything in the marketplace. And as we talked about those pioneers, Mr. Ellis has entered the building. He had some travel problems, and he arrived just about an hour ago, I think, so he is going to be bright-eyed and bushy-tailed, but Jonathan and I have a very great relationship. 4 years ago, about 3.5 years ago, he asked me to join the company as CEO. We were pretty tiny, but that's a lot of trust for an engineer. So I will always have a very special place in my heart for Jonathan bringing me on board. And with that, I'd like to now turn it over to him and let him give you a pretty fantastic look at what's going on with Cassandra itself. Jonathan?
Thank you, Billy. It's great to be in London with so many Cassandra users. Billy's right that there's been an explosion in Cassandra use just in this last year. And the reason for this explosion has been something that he touched on briefly. It's all about the architecture. Feng Chu at eBay summarized this in 3 points. That Cassandra gives you a peer-to-peer architecture. Unlike master-slave, there's no need for failover when things go wrong. There's no downtime. Linear scalability. and multi-data center support. And I think these three reasons are at the core of why Cassandra is the best choice for building Internet of Things and web and mobile applications today. And if I were to simplify that even further, I would start with that first one, that Cassandra's peer-to-peer architecture is where everything else comes from. So I want to dig into that just a little bit. In a Cassandra cluster, a client can ask any Cassandra node to route its request to the nodes that have the data. So in this case, I have 3 replicas that have the data I'm interested in. And the coordinator tracks, as it sends out requests to those replicas, it tracks how quickly they're responding. So it has an idea of which nodes are busiest at a given point in time. And so it can send that request to the replica that is least busy. If something goes wrong, though, and that replica goes down, then Cassandra can redirect that request to the next replica. We call this rapid read protection. That even though that replica went down, we can still finish that request without any downtime. So looking at what that looks like in a cluster, here I have a test 4-node cluster in laboratory conditions. And halfway through this test, I'm graphing operations per second of a read-dominated workload. Halfway through this, I killed one of the nodes. And this is what happens without the rapid read protection. That there's about a 10-second window until the failure detector realizes that, yeah, that node's down and he's not coming back. And then requests start getting redirected to other replicas. With rapid read protection, there's no window of downtime. We do take a brief performance hit because we had all those 15,000 or so requests that were in flight that now need to be retried all at once. So you do take that performance hit as that set of requests gets redirected to the other replicas. But you can see that the cluster recovers quickly and there's no period where no progress is being made. Now, one other thing that's interesting about this graph is that this green line representing the rapid read protection is not just better when things go badly wrong of I killed that node, but I'm peaking at a higher throughput. Not by a whole lot, but by a little bit. So what's going on there is that rapid read protection is able to retry not just requests to the node that failed, but whenever a request is slow because there is a GC pause on the replica, or maybe that replica just happened to have a load spike when my request got to it, I can retry those requests as well to another replica. So what this gives us is a system that gives you very reliable performance. So what I have here is this is a production Cassandra cluster we're looking at now. This isn't just my tests in the lab. Over a week of data, and the bottom line, the purple line, is my median response time, my average response time. So that's fluctuating between 700 and 900 microseconds. And you can see that this application has a periodic component to it, that when the users are awake and active, then there's more load on the system. So that's a normal part of this application. The top line here, the blue line, is my 99th percentile response time. So these are the slowest 1% of my requests. And those are still coming in at about 1,300 microseconds, so within about 50% of the average. So this is what Cassandra's peer-to-peer architecture gives you, is that since there's no bottleneck of a master replica, there's no single point of failure, and I can spread those requests out to whichever replica is responding fastest and deliver that consistent performance. So what I want to talk about today, I want to talk about 3 aspects of Cassandra 2.1. I want to talk about performance, I want to talk about data modeling, and I want to talk about operations. And I also want to spend a few minutes talking about Cassandra 3.0 and what to expect next year when we deliver that. So first of all, just in terms of generic read performance in 2.1, we've improved quite a bit over 2.0, almost 100%. The green line in the middle here is CQL for Cassandra 2.0. The orange line at the top is 2.1. So I'll give a little more color to this, that most of this advantage that you're seeing here comes from being able to group requests together between the Cassandra client and server. So we introduced a CQL native protocol that's optimized for CQL queries. And when you're using that native protocol, you can do asynchronous queries. So when your application needs to do 10 queries to load a page, it doesn't need to do a query, wait for a response, query, wait for a response. It can do all those requests in parallel. And so to get this performance benefit, you need to be taking advantage of that in the driver. You need to be able to take advantage of prepared statements in the driver. So I'm not saying that this is a magic upgrade to 2.1 and everything magically gets faster. You do need to be taking advantage of those advanced features. But when you do, then this is a realistic expectation, I think. The other thing I'd point out here is the blue and red lines at the bottom here. Those are the thrift performance numbers. So those have barely changed at all. So if you are one of the old guard of Cassandra users who started out using thrift, then I would say that the evidence in favor of switching to CQL is starting to get hard to ignore. One other thing about this graph is that this is very much a best case scenario. This is a scenario where my entire data set fits in memory. So I'm posting 200,000 requests per second. I'm not doing disk I/O. Everything's in the page cache. So let's look at a scenario now where everything doesn't fit in the page cache. So what we're looking at here is what happens during a compaction in Cassandra 2.0 when that doesn't fit in the page cache. So you might think this period at 90 seconds where the performance falls off a cliff is where the compaction started. That's not the case. That's where the compaction finished. So let me explain why that results in reduced performance. What's happening is during those 20 to 80 seconds where the performance is fine, it's performing the compaction, and the compaction is throttled. So if you've been around Cassandra for a while, you know that we spent some effort making sure that compaction won't eat up all your I/O. And so we can throttle the compaction down and say, OK, compaction, you only get 16 megabytes per second of disk I/O or whatever. So that works fine. We're keeping the performance between 80 and 90,000 requests per second while the compaction is going on. But when the compaction finishes, all of a sudden we now say, OK, Cassandra, start serving reads from that new data file that you just created and delete the old ones that are hot in the page cache. And so that's where that performance hits a wall, is when I'm now serving reads from that cold data file that is uncached. And then as we pull it into the cache, the performance gradually ramps up. So we deliberately ran this experiment on a spinning disk machine to give you a dramatic difference. So having it on SSD does mitigate this to some degree, but the effect is still there. So in 2.1, what we do is as we create that new data file, we start serving reads from it right away. As soon as we start compacting some partitions full of data out, we can start serving reads from those. And so there's no big bang where all of a sudden we've gone from hot data in the page cache to cold data. We're gradually heating up that new file as we create it. And so 2.1 gives you very consistent performance even through that compaction. Write performance looks similar in some respects to the read performance graph I showed earlier, where in the sense that 2.1 is almost 100% faster than 2.0. But there's an important difference, which is that the orange line of 2.1 here, it's mostly around 200,000 per second, but there's spikes of weakness down to 120 or so. And what's going on there is we're actually maxing out our commit log disk. So Cassandra is able to spread its data files, its SS tables, across multiple disks, but it's limited to a single commit log volume. So we're addressing this for 3.0. We're addressing it in two ways. One is by introducing commit log compression. So if I'm writing less data, then it's easier for the commit log disk to keep up. That's pretty simple. But the other is striping the commit log across multiple disks. So we've got a two-pronged attack to that problem. In the meantime, it is something to be aware of. This is a bit of an extreme case. It's a 32-core machine with 2 solid-state disks on Amazon. And so, be aware that as you push that core count higher and you push that operations per second higher, the commit log bottleneck might be something to be aware of. Finally, we've introduced a new compaction strategy. So we've had a couple kind of generic compaction strategies that you can throw at more or less any workload. We have size tiered, which combines SS tables based on how large they are and is better suited for write-dominated workloads. And we have leveled compaction that tries to guarantee that most reads will be served from a single SS table. So leveled compaction, because of that guarantee that it tries to provide, is much more aggressive about doing compaction and has much higher write amplification. So especially if you're trying to throw a high ingest volume at leveled compaction, it might not be able to keep up. So there's certainly scenarios, especially in time series data, where people want to have guarantees on their read performance, but they also need to have a high ingest rate. And so neither size tiered nor leveled compaction is a really good fit for that. So what we're working on is introducing compaction strategies that can take advantage of knowledge about the workload to specialize how they approach compaction and give you the best of both worlds. So date-tiered compaction is by an engineer named Bjorn from Spotify, and this is their approach for the time series problem. So what date-tiered compaction does is it says, given a set of data that's inserted in mostly chronological order, doesn't need to be 100% chronological, just mostly, and given the guarantee that once you insert it, it's immutable. You can't update it again, or my assumptions aren't valid anymore. But given those two, then we can do some interesting things. So the way it works is, as I write out new SS tables, each SS table that I write, by nature of the workload that I've told Cassandra about, each SS table is going to be mostly newer than the earlier ones that I wrote. So as I write those out, I define a window of time, and this is my the fundamental tuning parameter for date-tiered compaction. It's called base time seconds. It says how many seconds worth of SS tables do you want me to aggressively compact together? And as many SS tables as there are that span that window, I will compact all of them together. And it does respect the minimum compaction threshold, which defaults to 4. So once there's 4 SS tables, bam, I'm going to be on that. I'm going to compact that right away. And then I keep flushing new SS tables. They get compacted into their window, and so on. But when I get to the next window up, so like leveled compaction, where you go up exponentially in terms of you have 10 SS tables worth of data, then 100, then 1,000, date-tiered compaction works on a similar level in terms of these windows we've defined, where I have my initial base time in seconds, and then I multiply that out by my minimum threshold for the next window. So if my first window is 1 minute, and I have a minimum threshold of 4, my next window will be 4 minutes. The next one will be 16. The next one will be 64. So it will grow exponentially as well. And I keep grouping the most recent SS tables in my original window while this is going on. So if you have data that matches these assumptions, then you can get competitive performance on the ingest side, while also getting this guarantee that any scan that's within that base time in seconds will only hit a single SS table, or at most the minimum threshold SS tables. Now notice that this is actually available in 2.0.11 as well as 2.1. So our compaction APIs are stable enough that we were actually able to introduce this without making any changes to abstract compaction strategy or size-tiered or leveled compaction. So introducing this to 2.0.11 caused no stability concerns whatsoever. If you're still on size-tiered or leveled, it will behave exactly the way it has. If you want to experiment with date-tiered, then you have that option. If you do want to experiment, then there's a couple things you should be aware of. One is that the default base time in seconds is an hour, which in retrospect is probably way too large for almost any place you'd want to use it. So if you think about it, an hour is 3,600 seconds. If I'm writing 100,000 rows per second, that's 3.5 million rows that I'm asking it to compact very, very aggressively. So the trade-off is that the base time seconds defines the window that I'm going to get that single SS table read performance on. So in most cases, where you have an aggressive ingest rate, a window of 1 or 5 or so minutes is probably going to be adequate. The other thing to be aware of is that date-tiered compaction primarily optimizes a query that looks like this second bullet. Select, where, and then I give it a time bound. Now, I'm using a column named time here, but this doesn't actually need to be a timestamp or a date type. It could be a time UUID. It could even be sequential integers that follow a time-based pattern. But the important thing is I need to give it some kind of bounds between which to scan, and that will let the Cassandra Query Planner optimize that and take advantage of the date tiering that we've done. In particular, this third bullet, intuitively, as a human, you would expect that if you're asking Cassandra, give me the most recent rows, that implicitly that defines a window that says that first base time seconds window, that's the window I should be looking at. But the Cassandra Query Planner predates date-tiered compaction strategy by about a year, so we didn't build that in at the time to be able to do that. So that particular query is going to be optimized in 3.0, maybe in 2.1.3, but definitely not in 2.0. So just fair warning that that's a limitation there. So coming to data modeling, we've made some interesting improvements to data modeling in 2.1. In two areas in particular that I want to talk about. One is improvements to lightweight transactions, and the other is improvements to being able to denormalize your data more naturally. So lightweight transactions you're familiar with, we introduced in 2.0, gives you a way to prevent race conditions by giving your inserts or updates a condition. So if I have two users trying to create the Patrick McFadden account, I can give this condition if not exists, and Cassandra will make sure that only one of those gets applied. So simple, but single statement transactions have a certain limited usefulness. We can extend lightweight transactions across multiple statements within a batch, but to demonstrate that, I want to introduce another new feature. This was introduced in 2.0.6, so kind of midway into the 2.0 release cycle. And these are our static columns. So static column is a column that's shared across all the rows in a partition. So in this case, I have a bills table where each partition represents the bills for a given user. So by having a static balance that says I'm going to have one balance per user. And so what I can do now is I can have a lightweight transaction in a batch that simultaneously inserts a new bill and updates the balance. And so by wrapping that in that lightweight transaction, that prevents any race conditions where multiple bills are inserted and changing the balance in a way that one of the updates is unaccounted for. Now, a multi-statement lightweight transaction is implicit when you have a batch where multiple modifications are being made to the same partition. So since both of the update that has the lightweight transaction condition is affecting partition user 1, and the insert is also affecting partition user 1, they're implicitly part of the same transaction, so they'll be atomic. You cannot have transactions across multiple partitions, just within a partition. One more example. DataStax has a customer who needed an event log that provided a specific guarantee. They needed multiple producers and multiple observers in the log, but for business logic reasons elsewhere in the stack, bad things would happen if events were inserted out of order. So the normal way to do anything time-based with Cassandra is, well, just throw time UUIDs at it, right? And so that way no coordination is needed, everyone generates their own time UUIDs, and everything works fine. The problem with that is that since different machines have clocks that may be off by a millisecond or two, it's very easy, in fact, it's almost guaranteed that after an observer sees one event, that another event could be inserted before that, which is bad in this scenario. So what we did was we created a log that uses a static sequence ID to order the events. So we'll initialize each log by setting its sequence to 0, and then we insert events by incrementing the sequence, and in the same transaction batch, inserting the new event. So this makes sure that we can never insert an event that with an ID earlier than one that's already been inserted. So these two concepts, the static columns and the multi-row lightweight transactions, unlock some powerful concepts in this kind of data modeling that you don't need to reach for a zookeeper lock or a Redis lock or whatever, that you can do a lot of these linearly consistent operations using lightweight transactions directly in Cassandra. So the other thing that we focused on in 2.1 is letting you denormalize your data so that your data structure in your object model in your application matches your table schema. And so you can map one-to-one very easily from that object model to that row in the Cassandra table. So the key new concept here is user-defined types. So I can create a type. Here I've created an address type at the top that has several primitive fields and a collection of phone numbers. And I can take that type now and use it in my table definition. So I have an addresses map that includes this new address type as the map value. And yes, you can nest user-defined types. So if I have a map of addresses in Java, I can very easily turn that into a single Cassandra row now. Now, I'll call your attention to where that type is used in the create table. There's a keyword frozen. And what that means is that this type is serialized as a blob. So I cannot update just the city in my address, for instance. I need to replace that entire address with a new one. And so the 3.0 will support unfrozen user-defined types. In 2.1, only frozen are supported. But we require the keyword as a forward compatibility measure. Because in 3.0, we want unfrozen to be the default, so we're requiring the keyword in 2.1 now so that your code won't change behavior when you eventually upgrade down the road. We've also introduced nested collections. And I say that past tense. It's past tense in the code repository, but it's not actually released yet. So this will be in the 2.1.3 release, probably either late this month or early next. And so this works pretty much as you'd expect. You can have a map of maps of lists, a map of lists of sets. All of that is possible now. You still need the frozen keyword. Again, nesting collections is only allowed when the nested piece is frozen in 2.1. We've also introduced collection indexing. So here I have a songs table. I have a set of tags associated with each song. And I create an index on those tags. Now I can ask, give me the songs where the tags contains a given keyword. Pretty straightforward. So switching gears to operations. There's two pain points, I think, in existing Cassandra deployments that we wanted to address in 2.1. And those are counters and repair. So the pain point with counters in 2.0 and earlier comes from a design decision that we made early on, which was that in order to provide the best increment performance, we were going to write just the increment to the commit log. So when I increment my counter by 1 for the first time, I write that increment of 1 to the commit log. My counter value is also 1. I increment it again, my counter value is 2, but I write another 1 to the commit log. I decrement by 2, now my counter value is 0, but I write -2 to the commit log. So the implication that this has is that when I go and I flush this data from memtable to disk, then I need to update the commit log, and I need to mark the commit log and say, don't replay these increments because they're already in a file on disk now. The problem is that you can't mark the commit log and write the new SS table atomically. So what can happen is there's a narrow window where after I write the file and before I mark the commit log, if I lose power or I kill -9 the process, then next time Cassandra starts up, it's going to replay those increments that it's already counted once. So you can double count those increments. So the challenge for us in fixing this was twofold. First, we needed to fix it without going backwards on performance. And second, we needed to fix it in a way that we could still do mixed version clusters during upgrade. So we didn't want to force people to upgrade all their entire cluster to 2.1 at once. We needed to be able to start with a 2.0 cluster, replace one node, upgrade another to 2.1, upgrade another to 2.1, and meanwhile it's translating back and forth between these two types of counter operations. So that's why it was a tough problem to solve, but we were able to do that. And in 2.1, we write the entire counter value to the commit log. So instead of writing just the increment, now what's in the commit log matches what the full counter value is at that time, and replaying the commit log is now idempotent, just as it is for every other Cassandra update. So the way we were able to match performance while doing this, because we have to read the existing counter value, so we've introduced overhead that wasn't there before, is we promote hot counters to effectively atomic longs inside the JVM. And that gives us enough performance back to make up for having to read that value. So we benchmarked two scenarios because they do have different performance characteristics. One is a low contention scenario, which means that the counters that I'm updating are spread across many partitions. And so we have 2.0 in blue, 2.1 in orange. And you can see the 2.1's 5% or so faster at the high end, but more importantly, it's much more consistent. The 2.1 approach generates a lot less garbage, a lot less GC pauses, and gives you much more consistent performance. Now, in the high, notice here that I'm doing about 45,000 operations per second here in the low contention scenario. High contention, I'm only doing 7,000 per second. But my relative advantage over 2.0 is much higher because of that promotion to atomic long that I mentioned. So we were able to deliver a safer counter approach while meeting or exceeding the performance of 2.0. So it's a win all around. The other pain point that we wanted to address was repair. And the reason that we knew this was a pain point that needed some love, at DataStax, our support team logs for every ticket or problem that comes in, they log the cause. And repair got its own category. There's a lot of pain that comes from repairs taking too long. I'm not sure if my repair is finished correctly, and so on. And the root of the problem is building the Merkle tree that repair uses to synchronize. So how repair works is it takes the data for the table, builds a hash tree out of it, and they exchange the trees across replicas. So just like rsync, the first step is to check the hashes before we actually start sending any data around. So this is very network efficient. The tree is a handful of megabytes, up to 100 or so megabytes for a very large data set. So compared to terabytes of data, transferring this tree around is a small thing to do. The problem is to build that tree, I need to scan that entire data set. So if I have a terabyte of data to build that tree, it takes me 8 hours. If I have 2 terabytes of data, it's going to take me 16 hours next time. So as I add more data to the system, I'm still needing to scan everything to build that Merkle tree. So what I want to do is I want to scan just the new data. Once I've repaired a set of SS tables, they stay repaired, barring hardware failure. Because SS tables are immutable, we never update SS tables in place. We write new SS tables out with the new information. So those new SS tables are what we should be repairing. Now the challenges here were that to make this approach work, we need compaction to distinguish between repaired and unrepaired SS tables. Because if compaction starts mixing the two, then we have to treat the mixed ones as unrepaired, and we've lost our advantage. The other one is that a repair can actually encompass a piece of an SS table. So you can ask Cassandra to repair a specific range of data, and DataStax's repair service, for instance, uses this to do lots of micro repairs rather than one big repair intermittently. So when a repair spans a part of an SS table, then we need to split it up into repaired and unrepaired pieces. So if you're going to upgrade from 2.0 and start using incremental repairs, there's a couple steps you need to do to make sure it goes well. So full repairs are still the default. To opt into incremental, you pass the -inc flag. But you can't just jump in and start doing that, or it will say, oh, all those SS tables that didn't participate in this repair, I'm going to put them in the unrepaired arena, and now they're going to start over getting compacted from level 0 in your level compaction strategy. And so that's not what you want. That's not what you want to have happen. So the recommended way to upgrade is to do this. First, run upgrade SS tables to get everyone on the 2.1 SS table format. The 2.0 format doesn't know how to record repair metadata. Then you'll use the new SS table repaired set tool to mark those SS tables as being repaired. And then you'll run a full repair. So you're lying to it, and then you're turning the lie into the truth by marking them repaired before you actually repair them. And the reason you do that in that order is new SS tables are being flushed while this is going on, assuming that this is a live cluster. And so you don't want to mark SS tables as repaired that didn't participate in the repair earlier. So you mark them repaired first, then you do the repair, and if repair includes new SS tables that didn't get marked, that's fine, but the other way around would be bad. And once that's done, then you can start doing the incremental repairs. Finally, we've added support for Windows. And by added support for, I don't mean to imply that Windows is production ready in 2.1. We're projecting that it will be production ready in 3.0, but we've hit the big roadblocks in 2.1, and we're ready to get some wider testing. So the way I view Windows in 2.1 is that 2.1 is kind of an extended beta for Windows support. And yes, I know this is the old Windows logo. The new one's ugly. So for 3.0, I wanted to hit some of the highlights of what's coming up. Again, we've got a mix of improvements in data modeling, in operations, and in performance. Just to start on the operational side, we've had hinted handoff since ridiculously early versions of Cassandra, and since 1.0, it's looked about the same in terms of how it works. When a replica misses an update because it's down temporarily, or maybe it's overloaded and it's load shedding, we'll record that update as a hint to replay later. And so this is where those get stored in a system table called hints. It's partitioned by target ID, which means the replica that they're going to get replayed to. And then the payload is basically just a blob that we serialize that update as. The problem is that this is actually fairly inefficient. It takes at least 4 writes to insert and deliver a hint. Here's where I get that number from. When I first write the hint, it gets sent to the commit log, then it goes into the mem table, and then it eventually gets written as an SS table. So commit log and SS table, that's 2 writes. Then when it gets replayed, I write a tombstone marking it deleted to the commit log, that's write number 3, to the mem table, and then to an SS table, write number 4. Then finally, I can compact those together and reclaim that space from that hint that I replayed and don't need to keep around anymore. And by the way, if there's a lot of hints that are waiting to be replayed to other replicas, then those need to be rewritten as part of that compaction. So what tends to happen is that this hint design works fine when there's momentary hiccups due to garbage collection pauses or whatever in your cluster. But when you lose a node for several hours and you're constantly churning through hints, or you lose multiple nodes and you're writing hints for multiple targets, that's where this starts to make things a little bit fragile, because you're chewing up a ton of I/O compacting those hints back and forth. So for 3.0, we're introducing a specialized hint storage format. We don't need the flexibility that SS tables give us. SS tables give us random access. They give us the ability to do range scans. We don't need those. All we need is the ability to append a new hint and bulk deliver them. So that's what the format does. It's basically as simple as you can imagine. We have a file where we append hints into, basically like a commit log. We're just constantly appending. And we split that up by the target replica. So each machine that we have hints for, we have a different file for. And we actually break these up into files of several megabytes apiece so that we can do a little bit fine-grained hint delivery. But when we deliver the contents of a file, we just delete it. That's it. It's free. So this makes hints much lower impact on your cluster, and I think that's going to make a lot of operators very happy. Next up is we're introducing JSON support. So let me put a big red flag on this and clarify what I mean by that. I do not mean that we're introducing support for schemaless documents. If you have one document that has a user ID that's an int, another document that's a user ID that's a string, that's bad. Don't let anyone tell you otherwise. That's not a feature. So what we want to let you do is let you interact more natively with all the other services that speak JSON, because JSON's a great interchange format. It's a terrible schema definition language, but it's a great interchange format. So what we do is we leverage the existing schema that you have. So I have my address and my users table from earlier, and given a JSON document that corresponds to the ID and the name and the addresses fields, Cassandra will map that to a CQL row for you. So it's basically syntactic sugar that saves you having to deserialize that JSON message and then reserialize it out as CQL. But it's very useful syntactic sugar. We're also introducing user-defined functions. I'm not going to go into detail here because Robert Stupp has an entire talk later on today about the work that he's done on this. But just briefly, any language that can interact with the Java Java scripting API, that's the word I was looking for, you can write a user-defined function in. You can use those in a select query. That's the first basic set of functionality. We also anticipate being able to use them in indexes. So I can create an index using the value of the function result rather than the column value itself, and then query them by using the function in the where clause as well. Finally, speaking of indexes, we're introducing global indexes in 3.0. So the indexes that Cassandra's had since 0.7 are local indexes. So I create my songs, I create an index on albums, I insert some data. When I go and query that index and say, give me all the songs in the album Tres Hombres, I need to ask every node in the cluster, hey, do you have any songs for Tres Hombres? Because each node is indexing the data that it owns. So if I have 10 nodes in my cluster, I need to ask 10 nodes. If I have 100 nodes in my cluster, I need to ask 100 nodes. So you can see that this scales poorly. This is a good match for when you're doing a Spark job, and it's useful for that. But for an OLTP application, this is why we tell people best practice is the index can be convenient if it's a low volume query, but if it's a core piece of your application that you're serving 100,000 times per second, then this isn't the way to go. You need to denormalize that into another table so you can just grab the data you need from a single partition. So that's what global indexes does, is it automates moving that data into a single partition. It takes all the data corresponding to a given index value and puts that in a single partition. So now when I ask, what are the songs in Tres Hombres, I can just go to one node and get that data back. So that's a sneak peek of what's coming up in 3.0. And with that, I'd like to welcome Billy back for a few final words.
Thank you, Jonathan. All right. I want to take a moment just to thank our sponsors who make this event possible. And putting on something like this is never trivial, never easy, but they have all been amazingly supportive of everything we're doing, and it's great to have them here today, and I'm sure you'll see lots of different opportunities to interact with them, which will be fantastic. We want to really be great hosts for you today. So if you ever get disoriented or confused on where you should be, just right out in the back there, stop and talk to anybody at the tables. Take advantage of our Meet the Experts room. I can tell you in our US Summit, that was one of the most popular and heavily attended rooms that we had during the whole session. Go there and basically ask anything. Get a chance to really get into some good conversations. And finally, as I said, you're here today to learn and to share and to grow and to become a catalyst for this amazing future that you're about to write for us. So thank you so much for being here. We hope you have a fantastic day.